Okay, I decide to add some geometrical feature to our cooler geometry. What I'm going to do is that, see, here is our cooler. Okay, in the past, when we do the calculation, we have to, we only have the cooler, right? So we have to determine what happens at the boundaries of this cooler. Basically, we have natural convection over each surface of the cooler, which means say air is at a certain temperature, say 30 degrees Celsius, and because we have a low temperature water inside the cooler, so eventually the temperature of the cooler outer surface is also a little bit lower than the ambient air temperature. So there is natural convection over the outer surfaces of the cooler. But the problem is that then we have to figure out the natural convection coefficient over those surfaces, which means you have to use some empirical formulas to find the convection coefficient H value, so that we know how much heat gets into the cooler at each moment. This method probably is not the best way to do the work because we have to use those equations to do the calculation, and a more important problem is that we do not really know the cooler outer surface temperature, and those equations typically assume either the surface is at a constant temperature, it's isothermal surface, or the surface has a constant heat flux, and our cooler probably do not fall in either of these two scenarios. The outer surface is not of a uniform temperature, and I also do not believe we have a uniform heat flux over any of those surfaces. So it seems to me that probably the best way, the most natural way to do the calculation is to add a room. See, here we have this cooler at the very center of a room. Of course, it is either on the floor of the room or on a certain table. Here, in order to make our life easier, I assume the cooler simply sits on the floor of the room. Say if the cooler has a side length of 1 meter, I think probably it's enough to create a room of, I don't know, maybe how many meters? 6 meters should be good enough, right? Okay, I'm going to do that, but I'm not saying that this is the perfect number, optimal number. Then of course the room has, it's 3D, yeah. So anyways, so here I'm going to create another, okay, let me think. If I do that, yeah, that's fine. Okay, So I will create another box, or more precisely, I will create some other surfaces to represent this room, this big room with our cooler at the very center of the room on the floor, so that here I don't really need to take care of the convection coefficient here, because now I will also calculate the airflow inside the room, which directly gives us the heat transfer between the air and the cooler. So I will first create a few points. Say this point in fact is the origin, right? 0, 0, 0. This point is 0, 0, 1. So you know the sentence is 1. So I'm going to create some more points. 0, 0, 0, 0, 0, 1. So I want 6 in this direction. 6 minus 1 is 5. So I will have to have 2.5 meters in each direction beyond these 2 points. So 0 minus 2.5, that is negative 2.5. Here on this side is 1 plus 2.5, 3.5. So my feeling is that I should have okay, minus z equals negative 2.5, but I also need such a shift in the x direction, so x is also negative 2.5 and apply. Okay, now I have 1 point. Right now probably it's better to use the xz plane. See how it looks like. Okay, so this is the first point. The second point is x is still negative 2.5, but z becomes positive 3.5. Okay, yep. So the distance between these 2 points should be 6. Yeah, it says 6. Okay, distance is 6. Okay, then we go ahead. Right now we have 2.5 on this side, right? So we need 2.5 on this side, which means z is 3.5, but x becomes 3.5. Then I will create a point here. Okay, and then next point should be x is still 3.5, but z goes back to negative 2.5. Okay. Yeah. Now I have these 4 points. Probably I will need more points because I need 4 more points, right? For the ceiling of the room. Well, it not necessarily a ceiling, but it should be a surface which is high enough so that I can safely give it an ideal boundary condition at such a surface. Okay, I can give it a quite idealized condition with certain level of confidence that this idealized condition at such a high surface, which is so far away from my cooler, indeed is pretty close to that idealized boundary condition I'm going to give it. So if this is 6 meters, I guess I'm going to use like 10 meters along the y dimension, that is a height dimension. So here I'm going to use y equals 10. Apply. Okay, you cannot see that, which makes perfect sense, but it is there. Okay. Then 3.5. Okay, another point. Then I'm going to change x to negative 2.5. It'll give me another point. Then z to negative 2.5. The fourth point. Okay. Now since I have those points, I will be able to create some surfaces. Of course, here you probably can first connect those points to first form a few curves that might facilitate our creation of surfaces later on. So just connect those points. Okay. Now I will begin to create some surfaces. So create face. I'm going to use a method of from 4 points. I will still try to be consistent, so I will always use such an order, say a clockwise order, and I will always begin with a vertex of this room. So 1, 2, 3, 4. Okay, first 1, 2. Okay, it's difficult to see that vertex, so I'm pressing F9, rotate it, and F9 again, this point. Okay, F9 again. That's pretty much it. So 1, 2, 3, 4. F9 again. Rotate. Okay, I use a red right button to rotate the geometry in another plane. You know, this is what I do when I press the right button and then move my mouse. Then I hit F9 again. So this point. Okay, middle button. Okay. So basically the floor is created. I will create these 4 side surfaces. 1, 2, 3, 4. Okay, 1, 2, 3, 4. F9, rotate, right button. Okay, 1, 2, 3, 4. F9, rotate. F9 again. 1, 2, 3, 4. Okay, I also create this top surface. 1, 2, 3, 4. Okay, and pretty much I have all the surfaces I need. Obviously, again, I have to create 8 more parts to represent all these new surfaces, right? So here, how about I name the first one face, face what? Face floor. Okay, obviously the face floor is just these 4 new surfaces. Okay, face floor, and a new part called face room size. Okay, which contains these 4 new side. Okay, and I have a room top. Okay. Well, it's a pretty small room, I should say, but anyways,